All right, I hear some clapping from next door, and the timer has started counting down up the front here. So welcome along to session 4C this afternoon, bridges and civil structures. You're all a long way away. I wonder if anybody wants to hop up the front, make it a wee bit cosier. Please feel free. My name is John Tait. I'm involved in the Seaside Management Committee by virtue of being the Canterbury Structural Group Chair. And it is my pleasure to be your chair for this session. Got 4 speakers delivering papers today. If time permits, we'll try to get a couple of questions in between presentations, but if not, we'll just kick on through and try to catch a few questions at the end. So on to the welcomes. Welcome everyone, and I'd like to welcome our first speaker, Jamil Khan. Jamil is a technical director with Beca, has more than 30 years structural design experience. He's worked on several large civil and infrastructure projects like Mackay's to Peka Expressway and Peka to Otaki Expressway. He led the structural design of bridges on these projects, and today is presenting some of the innovative seismic design of bridges his team adopted on their recent project. And he's also chair of the Seaside Bridge Group in Wellington. So welcome, Jamil.
Good morning, everyone. Thanks, John, for the nice introduction. First of all, I would like to acknowledge my co-author, Laura Chen, and the rest of the team members who helped me in designing those bridges for these expressway jobs. Let me give the location of this project. If you look at Peka to Otaki is a part of the Capacities Expressway. If you see the bottom portion is Linden to Mackay's, that is the famous transmission gully, which is under construction, and we hope that it will be open to public this year. The next segment is Mackay's to Peka, which we designed and built, and it was open to public in 2016. And then Peka to Otaki is the current one where we're talking, and then Otaki to Lehman is a future. An outline of the project is a 12-kilometer alignment of expressway. There are 9 road bridges. 3 of them is expressway bridges. They're carrying the expressway over the rail track or Otaki River or Waitohu stream. And there are 6 local bridges which carries the local roads over the expressway. We have the 2 underpasses under the expressway, one for pedestrian, another one for vehicles, and then 5 share paths as a part of the cycleway and walkway. And the number of culverts, the pipe culverts, box culverts, CSP, you name the culvert, we'll find a culvert there in our project. This paper or this presentation is about the seismic design of the bridges. So the key parameter of the seismic pyramid listed here. The important thing I would like to bring to your attention is the return period. In infrastructures, we define the design earthquake as the ultimate limited state earthquake. For this job, like it is 2,500 seismic event, and that gives us the return period, R value is 1.2. Based on that one, bridge manual then you define your serviceability limited state earthquake, so which is 1/4 of the design earthquake level. That gives you RU value, which give you approximately about 100 years return period. And then is major earthquake or maximal credible earthquake we need to consider in our design to avoid the collapse mechanism, and that will be 1.5 times RU value of design, so which give you RU about 2.5, and that equates to 10,000 area event. Just to show the response spectra we use for the job there. So if you see the blue dotted line is the response spectra derived from 1170. And then we have the green dotted line, which is covered partly by the black line. That is the site-specific hazard assessment carried out by GNS. But bridge manual has a requirement that you can't lower your response spectra more than 30% of the code specified spectra. So that's why the blue line is drawn as a 30%. Sorry, dotted red line is drawn as 30%. And then the design, we adopted the maximum of the 2. Maximum of 2 means 70% of code specified response spectra or the site-specific hazard. So that's a blue line black line is covers the design spectra we adopted for the job. NZT also has a performance criteria for the bridges. We can find it in but important things I want to bring to the last line of the table, the acceptable damages. So for the serviceability limit, the damage are minors, sacrificial, but bridge should be operable. For the design earthquake, damage are acceptable, but it's repairable, and bridge should be able to use for emergency services within the 3 days there. The major earthquake was the damage are acceptable, but bridge can be used for emergency traffic after repair, and bridge can be reinstated for public use, maybe for the low load carrying capacity. So 3 bridges, I'm going to talk about the 3 bridges where we use some innovative seismic design concept or approaches here. Waitohu Steam Bridge, it is a 3-span bridge, 94-meter long bridge with a 24-meter wide deck, 3-span, and each span consists of 12 simply supported Super T. The RC abutment beams supported on an MSC wall, mechanically stabilized earth retaining wall. And Pier consists of RC crosshead, which is supported on a 1600 diameter columns, and each column is supported on a monopiles is 2.1 meter diameter. In terms of longitudinal seismic resistance, so if you notice that we have the bank seat and we create a back wall because bridge is designed as a semi-integral. So it is supported on a elastomeric bearing, but it's integral, so we eliminate the movement joint. And the back wall engage the soil to provide a passive resistance. And also back wall engage the bank seat. So when the seismic shaking came, the back wall engage the bank seat, both the front one and the tailing and back seat engaged, so we can utilize the friction on a bank seat between bank seat and the MSC wall. So for serviceable limited state, the inertial seismic force in combination with the in combination of active pressure from the soil and the soil earthquake load increment will be resisted by the friction between the bank seat and the MSC wall. For ULS limited state earthquake, because bank seat, when the friction was overcomes, the leading head will hit the soil and we mobilize the passive resistance from the soil. So for ULS limited state, we rely on the friction plus the passive resistance. For ME case, a major earthquake case, we have same as friction plus passive resistance, but we also have the from Pier resistance. So Pier provide a cantilever action, and they will resist there to provide additional resistance. In terms of transverse seismic elevation, we adopt a different ductility because we relying on the same as the system is resistance is coming from the friction as well as the Pier support column reactions. So we're using a ductility 1 when we're relying the friction, and we're using a ductility 3 when designing the potential plastic hinges in the portal frames. So again, if we have a VT, is the inertia force for per span, so for the serviceable limited state, the inertia force in the transfer direction will be resisted by the friction at the abutment. For ULS case, we'll get the reaction from the portal action. And for the ME case, maximum earthquake case, we add the additional fact, the overextend design of the portal. Again, so because it's a complex structure, we relying on the friction, and same time when the friction overcome, the bridge will be load resisted by the portal. So in order to this, then we did the upper bound and lower curves to check the sensitivity. So we analyzed the structure in 2 cases. In first case, we put a springs. We modeled a spring as a friction resistance from the between the soil and the bank seat, and apply that resistance. So in case that's one scenario. Then we determine, in next case, we ignore the friction that because the force is high, the friction is overcome, then whole load will be taken by the piers. So in that case, the bridge abutment is sitting on just on a roller, and we apply for whole forces in it, where in reality, the case will be in between there. So these are the two upper bound and lower bound cases we have adopted. The next bridge is Otaki River Bridge, which is the longest structure. It is a 33-meter long bridge with a 24-meter wide deck. It got 10 spans, and each spans we have 11 simply supported 1525 Super T beams. RC beams, the RC abutment is supported on the piles here. So this is different from the previous one. Previous one, the abutment was sitting on MSC wall, where now here we have a piles there. So abutment sitting on two 1800 diameter piles, and the piers. And pier consists of RC crosshead beams, which again, similar type the previous bridge. The 1600 diameter columns will support it on a 2.1 meter diameter piles. In a longitudinal direction, what we designed the piers to take the whole seismic force, because what we did, we decoupled this abutment and the deck. So deck is allowed to slide under seismic shaking, and whole load is taken by, because we have 10 piers, so pier will take the whole seismic load there. And they will act as a cantilever. So here's it, I just try to show the bending moment diagram that we can. Again, we use the ductility 3 to design the plastic hinge zone, and soil restraint along the pile length was modeled as a multilinear soil springs. If you notice that because our columns are smaller there, and piles are bigger, and plastic hinges are developing in a pile. So general rule is that when you have reduced a structure, you need to design for overextend. So what we designed, columns we didn't design for the overextend. Column we designed for the flexure demands. But the interface of column, we take the overextend shear developed from the plastic hinges. We make sure that the columns still have a shear capacity when the plastic hinges develop in a chain. In the transfer direction, again, the load is shared between it's different from the longitudinal direction. Here in transfer direction, we share, the bridge will interact between the abutments and pier, and load will be shared there. And so later load will be resisted by the abutment piles and as well as the portals there. And again, we use a ductility 3 to develop the plastic hinges there. This figure, I'm trying to show this thing because this is a different, the previous project we did. Previous project, we used a hammerhead, so piers are cantilever in a both direction. Here we have in a longitudinal direction, piers are acting as a cantilever, but in a transfer direction, because of this portal system, they will act as a portal. And when we analyze, we find that the demand at the top of the column is so high, and if we detail that, we can't detail for the reinforcement detail. And again, it's become a very stiff. So what we did, we induced a hinge at the top, and do the pushover analysis. So they try to push the maximum demands in the pile in the same location at the bottom of the pile. So if you can see in the portal frame, I have the two dotted line, the blue one and the black one. So black one matches with the same shape as what we're having. So we're getting within the same range, we get the plastic hinges. Otherwise, will happen that in a longitudinal direction, we'll be having a plastic hinge in a different location. In transfer direction, we'll having a different location, and then we have an interface between the columns. So by introducing a hinge, which we can control there, and we push the structure, which is still a structure within our allowable displacement, and then we mitigate the reaction. Try to have the hinges in the same location, because the circular piles, we provide the reinforcement, it has the same capacity. So it optimizes the design rather than having two different locations developing plastic hinges. Again, we have it's about 20 piles, and we want to standardize the pile design. So what we did develop an envelope for this soil structure interaction, and it came out as a demand and designed the pile for all the worst cases there, so that we have a similar, even at each pile location, we have done the proof hole, boreholes, but my friend, geotechnical engineer, cannot come out one single answer. So we did this thing so that we can get a single design which we can use for all this panel. And again, it was easy for construction, fabrication, so it is slightly bit conservative in some places there, but from the construction and production point wide, and the risk mitigation was worth we can do that. When we got this job, because this is a design and build contract, when we got a job that time, these piles and columns are the same size for 1.8 meter diameter. And you know that if the piles, they are constructed by different team and they have a different tolerance, whereas a column is a different tolerance. For piers and columns, we say, okay, we have a 10 millimeter tolerance in position, whereas a pile, they are 75 millimeter. So what happened if you have a same column, so one column move other side, the other column move the other side, and then you have a torsion in the beams, then you have the P delta effect, all those things there. So we sat down with the contractor, and I did a study, say, okay, we increase the pile sizes, we increase the more concrete, but reduce the reinforcement, and that's the balance how the net effect is 0, but it gives a more tolerance. So, but for example, if you see in the next page there, on the slide sheet, the pile is a 2.5 meter, column is a 16 meter. If pile is offset 75, we still have a room, the column to bring it the same position. And that minimizes any unnecessary P delta effect on columns, and also doesn't look the structure. If you're driving, you see the one column move 175 this side, the move 75 this side, people will always say, who's the engineer that one? The other issue is because we're using a smaller pile with supporting a large pile, there is no such guidance in the New Zealand standard, but we came to know that in Michigan State University has done some research, and they did some testing, and they came out that there is a failure because of playing action. There's a bars or the column can be pulled out from the column from the pile if the size is not properly confined. So they provided some guidance for providing confinement reinforcement, and we adopted that one. The next bridge I'm going to talk about is the School Road Bridge. It is completed now and is open to public, and it's crossed. If you see it crossed the exit, it will take over the local road from over the new expressway, and also on the existing rail track and the State Highway 1. The bridge form consists of, it's a two-span bridge. It's 83 meter long with a 12 meter width. Two spans, and each span has a 1.8 meter steel, 80 meter deep steel girders. It's a composite structure. RC abutment beams sitting on MSC wall, similar to the Waitohu stream concept bridge. And pier consists of two RC columns with a diamond shape, architectural design of a shape, supported on a 12 by 6 by 1.5 meter footing. In the longitudinal direction, again, we relying the friction and passive resistance against the back wall. So again, for SLS, resistant friction will be sufficient. Beyond and during ULS, we will be mobilizing passive resistance at the end. Because of this bridge we have the big back wall, so even ME case, the passive resistance was sufficient to hold the structure. So the structure is totally locked structure in this longitudinal. The interesting thing is here is the new idea we allow the deck to slide on the pier. We believe this is the first time we tried this concept there. So when the shaking transfer direction, the shaking will come, the deck will slide on MSC wall like the Waitohu stream, but also we allow we have the sliding bearing on a pier, so the deck will slide on a central pier also. So again, for the SLS case, we're relying on a friction. When the bearing has a very nominal friction comes up there, but bearing allows, but because we calculated how much displacement it allow, it moved, and we did the time history analysis, which I'm going to talk there. And this we have, beyond SLS2, the bank set will move on MSC wall, and MSC wall is able to accommodate the movement. If the requirement in the bridge manual is that you need to allow the movement for the 2 consecutive ULS case event or MSC event there. And the central pier is on, we put the sliding bearing, so that sliding bearing will slide, that will allow the bridge deck to move 500 millimeter. Even 500 millimeter, we put extra resilience that we have a scale we call is a Kipper ring, which engage the columns there. If the movement goes beyond this 500, and the column will engage, and column will take as a cantilever action. So in order to estimate the displacement, we use the time history analysis using the Newmark sliding block. In Newmark sliding block, an earthquake shaking record is applied to the model. When the friction resistance exists, the block moves relative to the ground, and this movement is aggregated as over the duration of the shaking. And this provides an estimate of the bank seat movement over the MSC wall for a given scale, given earthquake shake. So we use about 14 different records of size earthquakes from the different literature relevant to the New Zealand, and those we then to estimate our sliding on this. Newmark sliding block provides a reasonable estimate for the displacement, but unfortunately, it is unable to capture any resonance that may occur between the bridge and the shaking and the seismic shaking data. So that's what we did. We did additionally a time history analysis using the SAP model, model the bridge as a simplified structure, and then that is to account the mass distribution and the stiffness of the structure there. So in conclusion, there are several innovative techniques, seismic design techniques we have adopted on the job, and that gives us the most economical design and minimize the damage at the damage control limited state. Waitohu stream bridge deck is designed to slide on MSC walls and abutment. This is the first time, I think, the multi-span bridge are allowed to slide. Single-span bridges we have used on a same job, or other jobs like Hamilton Bypass we also use, but that's a single-span bridge which is allowed to slide. This is the first time we used it for multi-span bridge to allow to slide abutments there. Otaki River Bridge, we decouple this deck and pier, so the deck allows to move, and then pier will take this whole seismic, both transfer direction and longitudinal direction. And the school road bridge deck is designed to slide over the bearing and also on the piers. And the seismic design philosophy revolves that the abutment provides the resistance both in the longitudinal and the transfer direction. I would like to acknowledge the numerous contributions received from the Wakakotai New Zealand Transport Agency and the project partners and the suppliers in the development and implementing all these techniques for this job. Thank you very much.
Probably got a couple of minutes for questions if anyone has anything that they'd like to raise.
Thanks for the presentation. My question is about the expansion joints. How you designed, or what's the consideration for expansion joints as it's a slide and you have multiple bays?
Okay. Only on the Otaki River Bridge, because it's a 300-meter long base, that's the only bridge where we use the expansion joint. So we use expansion joint on both. It is a finger expansion joint. They were designed for the SLS movement. Beyond the SLS movement, they will damage and then repair there. The other bridges, that's the only bridge we have the expansion joint. Other bridges, we didn't use an expansion joint because that's why we designed for this. This is the new concept. It came out, if you provide a support on the bearings, so allow the beams rotation, and then you have a back wall which mobilize your friction to it. So day-to-day movement is taken by there. The back wall is moved there. It got a resistance from the passive soil, and you're allowed to movement there.
Excellent. Thanks very much, Jamil.
Okay, thank you.
I'd like to introduce our next speaker, Ronald Wessel. Ronald is Associate Bridge Engineer at Beca, based in Wellington, with New Zealand and UK Chartered Engineering qualifications and 15 years of experience in civil engineering structures in New Zealand and abroad. Ronald has had extensive extensive involvement in a range of civil structures projects in New Zealand and abroad, such as the Kapiti Coast, Mackay's to Peka Expressway, the Woolgoolga to Ballina Pacific Highway project, apologies to any Australians in the crowd, in New South Wales, post-seismic rail bridge repairs within the North Canterbury Transport Infrastructure Recovery Alliance, NICTA, rail bridge replacements across the North Island and various road bridge strengthening and upgrade projects for Waka Kotahi and local authorities. Ronald has been the project design lead for the State Highway 2, the award-winning State Highway 2 Wairoa Cycleway Extension project, and will provide an overview of the engineering challenges of the project, both in the design and construction of the Cycleway extension. So, welcome, Ronald.
Thank you very much. Good morning, everyone. Yeah, so I will try to only touch on some of the highlights and some of the very key challenges of the project. And if you've got any further questions, you will find some additional information in the conference paper, because in this 20-minute presentation, I won't be able to cover even everything I've mentioned in the paper. And not to mention all the non-engineering things like the consenting, the approaches, consultation with EV, and so forth, either. But if you've got any further questions afterwards, just ask me if we've got some time. Good. So here I also want to, before getting into it, acknowledge the various key parties for the project, which is Western Bay of Plenty District Council, main project sponsor of the project, who really been the party with providing funding, with support by Waka Kotahi NZTA, who also contributes to the funding of the project. Then Brian Perry, Civil, who were awarded the contract for the construction works of the project in cooperation with DC Structure Studio, who provided, in the end, an alternative steel truss design, which you can see on this photo. And I'll come to the difference between specimen design and alternative steel truss design later on. Just provide a brief background overview of the presentation. So I will just briefly touch on the background, how this project came about, then the key decision-making processes and considerations during the development of the design. Then I will briefly touch on the alternative steel truss design as part of the contract award to Brian Perry Civil. Then finally I will be talking about the construction challenges the contractor was facing, but which were known by us from the start. So and which we also had highlighted as part of the safety design process, and also as part of handover documentation to the contractor when during contract award, as well as highlighting constraints during the tendering process. So we try to be fair to all the tenderers during the tender phase. The Tauranga to Omakura to Tauranga Cycleway route is a key regional asset for cyclists and pedestrians in this region. And one of the issues of fully implementing this cycleway was trying to come up with a link crossing the Wairoa River, just south of Bethlehem. So just a bit of information about the bridge structure so that you can appreciate the difficulties we were facing during the design development process. This is a 7-span, 177 meter long, 7-span post-tension concrete bridge with post-tension concrete beams that have been made continuous over the pier locations. So with a continuous bridge deck at the pier locations, pile foundations, all driven piles, with using driven steel tubes, concrete infilled, a in-situ concrete pile cap that was then strengthened. The pile cap and the columns were strengthened in 2006 for improve on the seismic performance of the columns, and with really with very poor ground conditions. So in terms of seismicity, we're dealing here with subsoil class E, and I'll come to that in a second when I talk about the ground conditions themselves. So then there are also other constraints like major utility services. In this case, there's a portable water mains that's being also supported by the bridge structure, and other minor utility service, but this one was the main one to also accommodate in the retrofit design of the Cycleway extension. Ground conditions, so I mentioned subsoil class E, but it's, well, as expected in a river estuary, you're dealing with very poor, silty ground conditions, silty sands, down to a depth of 30 meters. So that's why, no surprise there that the pile foundations were driven more than 35 meters below ground level. And we carried out liquefaction analysis and lateral spread analysis, and we found that even under minor seismic events, this structure could be subject to lateral spreading and significant lateral spread movements, and we talk about meters of movements, which we also had to consider in our retrofit design. So, design development. So the task was set by Western Planetary District Council. Here's the existing bridge. Please add a cycleway to it. So we looked at various different options. So we tried to look at the simplest option is just clipping on an extension to the bridge deck itself. Unfortunately, as part of our assessment of the existing structure, we found that the deck didn't have sufficient capacity to accommodate a clip-on directly. So then we looked at clipping on a more substantial support structure or bracketing system to the crossheads and at diaphragm locations. But we also found that the columns wouldn't be able to accommodate any additional lateral loads, especially under unbalanced loading conditions. Then, that's why we ended up where we ended up. We then thought, okay, the only way how we can add an existing bridge to the a cycleway to the existing bridges by effectively bypassing the entire superstructure and the columns and transferring all the loads to the pile cap. Problem was, the piles wouldn't be able to handle the vertical loads. So what do you do? I'll come to that in a second. In terms of also other considerations apart from load path transfers, we looked at connectivity of the structure, because the cycleway is there to enhance connectivity between the two riversides and to provide more, to actually improve leisure facilities to the local community, because we have to appreciate that before the cycleway extension was installed, there was a limited way of people actually crossing the bridge, because the existing footpath is less than a meter wide, so it would be horrendously dangerous for pedestrians to walk on along a State Highway 2 with very limited clearance and no safety provisions put in place for pedestrians to cross State Highway 2 while you've got 30,000 vehicles per day crossing the bridge. So a really big safety hazard for pedestrians. And then also, we looked at providing a cycleway on both sides of the bridge because it would have some benefits in terms of future developments of the region, especially to, well, this north, basically the northeastern part of Bethlehem, just on the other side, riverside, because there's an adventure park, and it would have been good to make even at least a future provision for connecting a cycleway in the future from this future development onto the other side of the riverbank. However, money is always tight, so at least we came up with a compromise to allow future retrofit of an upstream cycleway on this bridge structure. And when you see the detailing, it becomes clear and apparent how this can be done. So this is basically the scheme we ended up with a downstream cycleway to provide at least connectivity on the downstream side from the eastern side to the western riverbank, and following through up to Umakura. So I talked about that the piles couldn't handle additional loads. When and what was the saving grace was considering pile setup. So I don't know whether everyone has, whether it's common knowledge. It was new to me before I read about this, and our geotechnical colleagues explained this to me. So basically, pile setup is a phenomenon that you would not usually use for the design of new bridges. And the reason for that is because pile setup depends on time-related effects of driven pile foundations in the ground. And what it means is when you drive piles, you displace pore water pressure and you locally increase the pore water pressure around the pile. What that means is it reduces your skin friction capacity. So when you do your rebound tests on piles, you always find that a couple of days or on the same day when you do a rebound test, you'll find you've got only a certain pile resistance which you can rely on for your design and to prove your pile capacity. However, over time, you'll find that this pore pressure, excessive pore water pressure, decreases basically what's also referred to in literature, the soil around the pile heals, it settles down, the pore water pressure equalizes, and you get a much higher effective stress within your soil, which then increases your friction capacity in your pile. Hopefully, I've explained it. Simple enough. And we utilize this, and we managed to effectively increase the pile, or we could justify an increase in pile capacity of 50%. So, and this in the end then made the third concept viable. So we solved the problem of transferring the load to pile cap level, and we could prove also in conjunction with having consulted with the previous geotechnical engineer who provided the previous assessment of the piles, that we could increase the pile capacities. So we had now a viable solution. Seismic constraints, I want to touch on very briefly. We basically had to consider the circumstance that we're dealing with a continuous structure because it's post-tension beams make continuous over the piers, and effectively it works as one big diaphragm or strut in the context of lateral spread. So when you want to keep the fabrication installation of a cycleway truss simple, and you want to install a series of simple supported trusses, you're dealing with, at first, an incompatibility between a continuous structure, which can act as a strut, and many separate single spans that could be squashed together like an accordion. So, under lateral spread effects and significant longitudinal seismic demands. So therefore, what we did, we provided a series of mitigation measures. One of them was provide a fuse at the abutments so that basically the back wall could shear off the piled bank seat, and behind the bank seat, what you've got there is polystyrene, so very lightweight material, something that will not provide any resistance to the trusses and to the bank seat when you see major displacements. So basically, what it means, the bank seat and can basically move a significant amount. We're talking about meters here, while the trusses are, or the intention is that the trusses are protected under this very significant lateral spread movement. So further things we also had to consider were seismic gaps at SLS. So you can see we've provided seismic gaps between the back wall and the end of the trusses. And another important thing to consider is separation of seismic articulation. You've got basically a monohead pier that will behave like a lollipop and will possibly hinge at the base, where you've got a pier frame that is quite rigid. So hence we had to design the pier frame transversely for a ductility of 1, whereas compared to the existing bridge, which was assessed under ductility of 3. So you're dealing with also a incompatibility of displacements in the transverse direction, which we mitigated by providing seismic gaps also in the transverse direction. So really, it's to provide harmony between the existing bridge and the retrofit was about providing seismic gaps and fuses in different shapes and forms. Since it's a lightweight structure, we also considered human-induced vibration, by considering vertical acceleration and lateral acceleration effects. And we've basically used the approaches provided in the bridge manual. And we found that with the specimen design, which was an FRP truss, we found that the frequency was slightly below the 5 Hertz threshold as stipulated by the bridge manual. So again, I could talk about the approach that we took by assessing the vertical accelerations. Perhaps later in the question answer session, I can elaborate further on this. But when it came to the tender design and the alternative steel truss design, it actually was found that, and one added benefit of going for a steel truss was the increase in frequency, because the steel truss was, due to just its Young's motors compared to the FRP, just way stiffer, and hence the frequency in this case also was greater. We also carried out lateral vibration checks in accordance with the bridge manual, which cites the National Annex of Eurocode 2. And we've checked for lateral locking stability. Basically, we looked at the ratio of structural damping and provided for the structure for lateral movement effects. As you may appreciate, that you can get out of balance effects. Perhaps probably a very good example is the Millennium Bridge, where lateral excitation effects were very apparent. And yeah, so another key consideration were the design of tubular connections. And they were all bespoke. Unfortunately, there's no HERA design guide who can provide you any significant guidance. So we basically had to go back to first principles, had to look at how can we make these connections or design them in a robust fashion. And you will find the common theme of all these connections were stiffness. So we provide stiffness where we could to avoid localized buckling of the tubular connections. So, and this is what happens if you either exceed the load in a tubular connection or you don't provide stiffness. You're basically you're generating localized buckling in the connection or punching shearing. So fortunately, the French have come up with some really good design guides on how to design tubular connections, issued by CIDECT. And although we bend back to first principles, in these guidelines there is a lot of useful information about pointing out to effects or considerations that you wouldn't even be thinking of, like localized stress concentrations in certain weld regions when marrying up, for example, a inclined cut tube with a steel plate. So you can see basically in the top you can see where these two CSH sections come together and meet with a plate. For example, there in the lower part of the tube, basically SIG guidelines highlight to you that you were dealing with over proportionally higher shear stress concentrations in your welds, which normal linear elastic analysis wouldn't tell you to consider. So that's where, so when it comes to these sort of very bespoke considerations, that's where the SIG guidelines came in very handy. Truss design, because I'm just noticing I'm just running slightly over time. So there we went from an FRP design, which was provided by one of the FRP suppliers in New Zealand, Wagner's, who were during the consultation and pre design phase very helpful. So during the tender evaluation period, Brian Perry came up with an alternative steel truss design. And in this case, it just purely came down to cost. So just a couple of things to mention. To coordinate the alternative truss design with the substructure design provided by Beca, we did a lot of 3D modeling and coordination in this way. And in terms of the connection design, the steel truss designer, Dan Crocker from DC Studios, actually made use of finite element modeling in conjunction with the rules and design guidelines by CIDECT. So in this case, you're dealing with a lot of nodes, so there it actually makes sense to invest more time in trying to model a node, whereas with the substructure nodes, you're dealing only with a very few very high-loaded nodes. There we thought, we basically took a more robust, perhaps some say a more conservative approach by just applying, specifying stiffness to an extensive degree. And this was basically the result between the tender design and the constructed works. So you'll find it's nicely matching up. So I'll just briefly touch on construction challenges. Obviously, the main was really the center of gravity of the pier, and there you could see basically it would have been very difficult to lift these V-pier halves from bridge deck level, because you would have needed some very extensive temporary works like a counterbalancing frame in order to lift it in from above, because the center of gravity just sits beneath the bridge deck. So the innovative method here was using a barge. So basically, the V-pier halves were floated in, and then the tidal ranges of the estuary were used to provide, to lower the V-pier section halves into place and then connect them up. And this was the installation of the Cycleway trusses in a more conventional way using a tandem lift from bridge deck level, which was more straightforward, but still needed a lot of planning and temporary works considerations to avoid localized overstressing of the bridge deck and the crosshead column connection. So therefore, for example, Brian Perry looked at minimizing maximizing load spread of the outrigger loads of the cranes, and using the smallest possible cranes in order to minimize the outrigger loads onto the bridge deck. This is the final product, and yeah, it has been quite a success, not only by measured in terms of performance and delivery, but also the feedback that we have received from the local community. They have been absolutely, they've been praising this project in terms of the use they can get out of it, and the high level of connectivity between the two riverbanks for cycling and for walking. And yes, that's my presentation. Any questions? Unless we've got some time. Yep.
All right, thanks again, Ronald. I'm sure it's much more fun to jump off as well as cycle over. I like the fact that you had the rope swing still in the shot there. So Alex Vink is our next presenter. Alex is a senior structural engineer at Tonkin & Taylor. He's a chartered professional engineer with a practice area of civil structures on infrastructure projects. He's been involved in a wide range of engineering projects throughout New Zealand, including the State Highway 20 Waterview Connection, the upgrade of the Puke Ahu War Memorial Park, the Waitangi Wharf Upgrade Project, and City Rail Link. He was a lead structural engineer for design of Te Wananga. Welcome, Alex. Cheers.
Thank you very much, John, for that wonderful introduction. So I'm here today to talk about the design of Te Wananga, which was an architecturally designed wharf which serves as a public space in downtown Auckland. Just really quickly about myself, senior structural engineer at Tonkin & Taylor. I was the lead structural engineer for the design of Te Wananga, and I've been involved from concept design back in 2018 to the project opening, which was on Friday. Just a very brief run through on what I'm going to be talking about today. I'll start off with the project context and location before moving on to the design intent and form, touching on construction sequencing, then taking some time to talk about the structural analysis, the seismic design, the technical challenges, and then I'll finish up with conclusions, acknowledgements, and maybe some questions. So I'd just like to take us back to 2019 at the start of the design process of this project. So this is Quay Street in downtown Auckland, the iconic ferry building in purple with the arrow pointing there. So Te Wananga was delivered as part of the Downtown Infrastructure Development Program. So this was a series of projects delivered by Auckland Council and Auckland Transport using the early contractor involvement model. So this Te Wananga was linked to a number of other projects, including the Quay Street seawall strengthening. So this was this Quay Street seawall is a 100-year-old heritage wall and is roughly located in that along that blue line there. The Quay Street enhancement project also happened in the same location. This involved the transformation of four car lanes into a pedestrian promenade, a cycleway, a dedicated bus lane, and then 2 car lanes. The ferry basin development was also part of the Downtown Infrastructure Development Program, and so this involved the creation of 6 new ferry berths. And then in the red here, we have Te Wananga. That's the approximate extent of it. Te Wananga came about following the sale of the Queen Elizabeth Square for the Commercial Bay development, which is just up the road. So Te Wananga takes the form inspired by eroded sandstone shelves. It's intended to provide a space for rest and a better connection between downtown Auckland and the Waitemata Harbour. It takes the architectural form of a coastal forest of Pahutakawa and has a number of marine ecology elements in the design as well. I'll just touch on the structural form. So Te Wananga is a highly irregular 1,600 square metre concrete deck slab supported on concrete piles. The slab is nominally a flat slab deck, so the entire deck has a constant soffit level, but does have drainage falls built into it by varying the concrete thickness, as well as a step which roughly follows the green line. We also had 6 planters that were made from steel and suspended from the deck. I've highlighted 2 in the blue circles. We also had 3 openings in the deck. I've circled one in yellow. This provides a spot for people to view the water, as well as some of the marine ecology elements. We also have a number of kupenga. Now, these kupenga are woven rope nets that provide a place for people to sit and lie down and get close and enjoy the water. We also have 9 fender piles. They take a slightly different form to this concept level render, and about 50 mussel floats, which provide an area for mussels to grow, with the intent being to improve biodiversity in the downtown Waitemata harbour and also to improve water quality. I'll give a really quick overview of construction sequencing because it governs a number of the key design elements, which I will explain later on in the presentation. So here we are in March 2020, about halfway through the piling. So the piles are fairly conventional marine structure piles, steel casings driven to rock, then augered out, and then tremie poured. Then the deck is constructed in situ on a number of false work platforms, moving progressively from right to left. You'll see in the second pour there towards the top end of the slide a rectangular box out. This is where one of the planters ends up. This was done in a 2-stage pour, so we've got a small concrete slab at the start there, planter gets dropped in, and then concrete poured later on. So pour 4A and 4B were split into 2 at the step edge to improve constructability. And that's the second stage of the planter, for the first planter going in, installed with some temporary works. The final 2 deck pours. Then following the installation of some balustrades, a overland flow stormwater grate, and some planting. This is a shot of Te Wananga a couple of weeks ago at the Dawn Blessing. Still some steel balustrades to be installed at that stage, but about 98% of the way there. I'll now get into a bit of the detail on the structural analysis side. Te Wananga was designed as an importance level 3 structure with a 50-year design life, but detailed with a 100-year durability design life. Little plug, we use SAP 2000 for modelling. And the deck was modelled as shell elements, the piles and planters modelled as frame elements with rigid connectors between the planters and the deck. The geology at the site is quite important. It consists of very soft marine siltstone called Tauranga Group, which overlays weathered East Coast Bays Formation sandstone and then sits on top of competent East Coast Bays Formation rock. So during the design, we considered soil structure interaction by modelling the ground as a series of nonlinear load displacement, or PY curves. And due to the highly irregular form and the irregular geology, the nonlinear static procedure or pushover analysis was used for seismic design. For those not familiar with seismic design approach for wharves, very similar to bridges, much that the hinges form at the column head and in the ground. I appreciate many of you will be aware of this, but I'll just touch on pushover analysis really briefly as well. So pushover analysis involves the selection of hinge properties based on detailing within the sections, modelling of nonlinear elements. So in this case, it was just the soil structure interaction and the hinges themselves. Then applying an increasing force of increasing magnitude until hinges reach the prescribed rotation limits, and then comparing the displacement at these rotation limits with the target displacement, with the displacement of the target node, which I've circled in purple, roughly at the centre of gravity of the deck, and comparing this to the calculated displacement for the design level earthquake using a spectral displacement curve. So this image here shows hinges forming in the direction parallel to the seawall, colours representing different plastic rotations. Just a few overview on some of the ULS stats. Displacements, depending on the sensitivity assumptions, ranged between 125 and 225 millimetres. Our ductility was in the order of 2, and our period sat in and around that 1 second mark. Now, the reason for such a wide range in displacements and periods is down to the sensitivity analysis. So we looked at, in the design, the effect of the steel casings. The upper bound stiffnesses were based on assuming that the steel casings had not corroded and were completely composite with the concrete piles. And then the lower bound was on the basis that they'd corroded away entirely. We also looked at the variable geology in the design stage. We recognised pretty early on that this was one of the biggest risks to the program. And so what we looked at was varying thicknesses of, say, the East Coast Base Formation mantle. We also looked at having a sharp fold in the rock itself. And so these effects sometimes induce some pretty torsional modes. But by considering this in the design stage, when this came into play on site, we were able to say very confidently that we'd considered this and that we didn't need to do any redesign on site. I'll now run through some of the technical challenges. I think one of the bigger challenges was the deck slab itself. Being a highly irregular jointless slab, about 80 by 35 metres. So this was, again, this had a flat soffit, so had drainage falls built in as well and a step. And so the reason for this form, I recognise many of you probably thinking this is an unusual way to build this sort of a structure. The early contractor involvement was that a flat slab would be cheaper and quicker to build. So what we have actually is the deck slab thickness was governed by overstrength considerations as well as pile bar anchorage at the thinnest section of the deck. And what this means is that the deck is far thicker than it actually needs to be for structural reasons. So it's ranging from about 0.5 metre to 1 metre thick. And what this also leans to is that the secondary effects really govern the design, particularly for crack width. So we found that the differential temperature case and the absolute temperature case were pretty severe. In fact, with the differential temperature case, some of the outer piles, due to slab curling, were being pulled into tension. We also had to look at deck shrinkage. The really large volume of concrete there put some pretty large tension forces and bending stresses into the deck slab. And these were exacerbated by the constructor's preferred sequencing. In effect, when moving sequentially from right to left, the old concrete pours effectively restrained the new ones, and these introduced some very large tension forces at the construction joints. Also, the planter sequence added additional bending stresses just due to differential shrinkage between the second pour and the first pour itself. The end result of this is a pretty substantial amount of reinforcing. I worked it out quickly. It's about 400 kilos of reinforcing per cubic metre of concrete. So this shot here shows the planter to the right, boxed out there. Another shot here shows a planter on the left, and you can see the curved irregular deck edge on the right all formed out. And this is a close-up of the beam column joint, which was very heavily congested. Another really interesting technical challenge were the suspended planters. So these planters are made from mild steel and they're hung from the deck. And the reason for this was, again, ECI feedback was that it would be cheaper and quicker to suspend the planters from the deck rather than to do a more conventional piled solution. So the steel planters take the form of, the base has a top and bottom flange and then a series of web stiffeners running in orthogonal directions. The steel walls themselves span horizontally between the vertical stiffeners, and then the walls span vertically between the bolts and the base. Now the bolt groups, we had 112 groups of bolts, all up about 1,500 M24 bolts that have been designed to be composite with the deck slab. And there are a number of material selection challenges that were made not just by us as the engineers, but the wider project team, so the architects, the constructors, and the client themselves. And so there was a trade-off there between efficiency, aesthetics, constructability, marine durability, and then maintenance and capital expenditure. The end result is a series of mild steel planters with high-spec thermal spray zinc coatings on the exterior faces and an ultra-high build epoxy on the internal faces. Another real interesting challenge was the installation of the planters themselves. So this is a shot of the planter hanging in place before any bolt holes have been drilled. So the intent here is that the planters would be lifted into place, then a site measure of where the bolts could physically fit within the reinforcing. So when we designed this, we recognised this and gave higher than conventional construction tolerances. But unfortunately, most of the bolt groups, they were able to work within the tolerances, but unfortunately, there were a few that couldn't. So this involved some rapid redesign on site, basically, and usually same-day turnaround for us. Then the planter is removed, holes are drilled, coatings are all touched up, and then the planter is lifted in place, bolts are installed, and then the second stage concrete pour. So this shows the finished product. Another real interesting challenge with the planters was trying to estimate both the weight and the wind area of a tree. So what we did with this is we spoke to our project arborist and asked them to point out 3 or 4 trees that were in and around Quay Street that would mature and would represent what they thought would be the final size of tree. Then we had the 3 larger ones scanned, and we whipped out based on this we had a volume of wood, which we were able to use to estimate the weight, and a surface area of leaves, which we were able to use to estimate a wind area. So this is a shot of Te Wananga on the opening day last Friday. The project vision, in my opinion, presented a number of really unique and interesting engineering challenges. But with the commitment of the entire project team, I think we were able to turn the architect's vision into a reality. And I believe we've delivered an outstanding result and an enduring legacy for Aucklanders and those who visit the city to enjoy for generations to come. Just before I wrap up, I'd also like to acknowledge our clients, Auckland Council and Auckland Transport, and thank them for their support and their vision. And I'd also like to thank our project partners, ISMIS, the Downtown JV, and the Mana Whenua Working Group. And I'd also like to thank ISMIS for use of their renders. Thank you.
Right, Liam's very kindly caught us up, so does anyone have any questions for Liam's talk?
Alex.
Oh, sorry, Alex. Liam's next. I have one question. What was your maintenance schedule, or what was your maintenance requirements on those steel planters?
That's a good question. So in terms of, you're talking about the coatings themselves, or?
Well, the coatings, yeah. So like your epoxy coating, does that ever need to be inspected and addressed at all? Yeah,
so I think the critical thing there, we did make allowance for corrosion loss, particularly for the retained face. It's not as severe an environment as, say, the external face. So we have put, for example, on the bolt heads, we've put a bunch of grease and some additional plastic caps to try and provide a double corrosion protection system. We've also highlighted this in the maintenance manual, or we will highlight this in the maintenance manual. It's still final documentation is being completed, but yeah, we will be highlighting that. It's not too hard to dig down a couple of 100 mils to expose a bolt and see how it's going. And then for the external faces, look, there will need to be some maintenance with thermal reapplication. It's hard to estimate an actual design life. I mean, we think it's somewhere between 20 and 40 years realistically.
Any other questions?
How close did you come to the steel limit for the concrete slabs?
So we did have to stagger laps to avoid over reinforcement of the slabs. So I think if we had all our laps in the same location, yeah, that would have put us over the limit. But I think we're a little over half.
Seeing
So when you say, have we considered using well, I guess steel there, changing the structure type to say steel instead of concrete, they would have had some pretty significant aesthetic implications from the architectural side, and I think also a bunch of maintenance requirements as well. So I think this was discounted pretty early on at the concept design.
Who was your contractor?
Sorry?
Who was the contractor?
The contractor was the Downtown JV, so that was made up of Hebs, Downers, Sodtange Boshi, and I think JFC is a major subcontractor.
How does construction monitoring work with that much structural or reinforcing steel?
Sorry, what was the question?
How does construction monitoring work with that much reinforcing steel?
So construction monitoring is quite a challenge with that much reinforcing steel. One of our site engineers was I joked that he almost lived there and could probably just try and rent a place in the steel itself to try and sleep there. Yeah, he was down there most days when they're doing the deck pours, and obviously you can't come back at the very end and go and then figure out whether they've done everything correctly just from looking at the one shot at the end. So it was a gradual process.
Fantastic. I think we'll wrap it up there and move on.
Yeah, I'm happy to take more questions outside of this. If anyone just wants to talk, just come and grab me.
Thanks, Alex. Cheers. Liam is a Senior Associate and Chartered Engineer at Beca, based in the Hamilton office. He has 12 years of experience in the design, assessment and construction of civil structures and bridges. Liam returned to New Zealand in 2019 after residing in the UK for 3 years, where he worked on a mix of large-scale road and rail projects. Prior to that, he worked on large-scale design and build type road and rail projects within New Zealand. And Liam has a keen interest in implementing parametric and digital engineering design tools and aims to adopt an off-site construction and design for manufacture and assembly, DfMA, approach in his work. So welcome, Liam. Cheers.
Cool. Kia ora tātou. Thanks for the introduction. Yeah, my name is Liam, and hopefully here to share some learnings from a bunch of projects I've worked on, and I guess a slightly different way of approaching design. So I'm going to talk to you, about challenges of some delivery with some infrastructure projects, talk about what DfMA is, the term. Perhaps in New Zealand it's not really a term I think that's common. Talk about what are the benefits of adopting a DfMA approach. How would a DfMA approach be applied, or how does it work in with our normal design process? A bit of digital engineering as well in there, and also some examples which I'll show as well in a summary. So I guess I threw together a bunch of what are some challenges we have in our design and construction. And our designs are generally bespoke. They're not automated. There's not a lot of ability to cope with change. They take quite a bit of time. On some projects we spend years in the design phase. We've probably within the industry we've got relatively low levels of research and development. A bit of lack of knowledge and sharing. Also, health and safety can also be improved through our designs. Typically, construction costs are high. I think we have a lot of headlines. There's always project budget increases, particularly on big infrastructure projects. And also we have relatively long construction programs as well. So those are some issues I've come across, and probably you guys have as well. So one thing, the New Zealand Construction Sector Accord was established a few years back, and they've got some aims at trying to solve, or obviously we want to better the construction industry. I guess we can, as engineers and contractors, we can contribute to this. We want to increase productivity, we want to raise our capability of our own internal teams and the profession as well, improving resilience and restoring confidence. And I think, yesterday morning there was quite a bit of discussion on these topics around the competency of engineers as well, and the perception of the public on our profession. So if we were trying to achieve some of things, how can we actually do that? How can we improve our delivery and productivity? So streamlining designs, approaching construction in an off-site manufacture sort of way rather than on-site. So we want to actually reduce our time spent on-site. We want to reduce our health and safety risks. We want to be able to innovate in our design and construction methods, to actually improve the reliability in terms of program and cost as well. And I think a massive key thing, or what I've learned, is you need the right input at the early phase, the concept design. That's when you do all your hard thinking. That's when you usually think of what is the solution. And if you get that wrong, or the wrong input at that early concept phase, you're setting yourself up for a lot of challenges down the road. And so what I'm saying is we can apply a DfMA approach, design for manufacture and assembly. So I'm sure you guys are thinking, what is this DfMA approach? Essentially, it's looking at maximizing off-site works and minimizing on-site construction. And the reason why we want to do this is we want to gain objectives, gain benefits in program, reducing risk, safety, environmental, and quality as well. And so this is kind of similar, I guess, to say modular design or off-site build, which is, I guess it's more common in the buildings world. I'm a bridge engineer or civil structures engineer, and it's not quite there yet. But yeah, so there's some standard principles that I guess a way of, or a design approach, looking at standardizing components, and we do this relatively well in some applications, trying to reduce man hours on site. I think, do we think we want to reduce people on site in our designs? Probably not. We want to have a product-led delivery. So what products are available in the market that we can use in our design that the supply chain has already set up for us to use? And I think the product-led delivery is a key thing around design for manufacture and assembly. You want to design something that can be manufactured in a warehouse or in a yard, and then brought to site and assembled, and it's going to work. And having products, that's one way of doing that. You definitely need contractor input. They're the people that are going to build it, producing products. At the start of design, you want to increase construction efficiency, have less wastage on site. Key thing is obviously you want to produce workable designs and details. And also you want to have designs which are less subject to error. And also, you need to have collaborative design at the early phase, integrating all stakeholders. So some key benefits here. Health and safety, I think, is a huge one. Just by moving people into a off-site or a yard, or inside even potentially some factories, there's a lot of health and safety benefits. People are working at table level rather than maybe bending over. They're not working at height. There's a whole bunch of benefits of working in a more controlled factory environment. So precast concrete, for example, brings a lot of those benefits. So also, fewer on-site movable plant. People are subject to that. Usually you'd have a number of stages on-site which require a lot of movable plant. If you're doing that off-site, that also reduces that. And there's definitely reduced trip hazards in more controlled environments. There's usually the health and safety aspects are usually addressed a lot more than on-site. Obviously, there's a lot of quality benefits. If you're working with concrete, generally you've got to improve the quality of the concrete. And if there is bony concrete, you can fix it in the shop. You'll see it rather than it's being hidden. Precise positioning of rebar. Obviously less chance of defects. And also, usually when working in this sort of way, nowadays we're using to use 3D digital design for all of the components, and that allows you to enable some clash detection as well on elements when you're building your whole bridge or whatever structure in 3D. You can understand how things fit together and try and work out what those clashes would be. You want to have repeatable units. If something is repeatable, there's a lot more efficiency in it. You also want, generally from what I've seen in some projects I've worked on, there's the costs are similar. So if you're looking at trying to maximize off-site construction versus in situ, but actually you're going to get some significant program benefits. And this is why we're seeing more and more buildings and civil structures using, components to build the bridge rather than just fully on-site built. And also, there's obviously some key areas of less risk around concrete delays on site, weather delays, etc. So, in terms of DfMA for bridge design, how do how can we take factory production methods, which, you know, in like a car industry, for example, and actually do that for bridges? I think that's a question we're challenged with. You know, what sort of systems and tools do we have to enable us to actually work and develop these types of designs? Is there a design and construction technology that we're just not even using that is around, but just because we're not, you know, we don't interact with those types of groups? So how can we share knowledge more to actually increase this and take learnings from other engineering disciplines? And also, how can we look at optimizing our designs against a whole bunch of different constraints to increase repetition of design? So I think these are some, I guess, questions around what we're trying to achieve, but how can we start working towards them? Just a quick slide here on actually components. So looking at, you know, a bridge is made up of a whole series of parts, as all bridges, all structures are. And usually you know, you develop your component or a bridge based on what are your material requirements around durability, strength, etc. What does that bit need to do? What's its functional requirement, and what does it need? What size is it? What's its geometrical requirements? And trying to put that into some sort of systematized family or repetitive element. So I guess the DfMA design approach, on the top here, we've got typical design process where, you know, at start of design, working from the left to the right, you've got your site constraints. What do you need to achieve? What are your requirements? What are some options of what are you going to do? You then work it into an options report, typically for bridge structures. You talk to clients and stakeholders, get their input. Then you move forward with, you know, choosing a single option after you've done that optioneering, moving into detailed design and construction. So with trying to implement a DfMA approach is, rather than having that top line where typically the consultant and the client generally do all that work, can we look at what are common design repeatable elements or components at that early phase? How do those components fit into possible bridge forms or structural forms? And what types of families are there or components that we can look at? And all that should all be feeding into your initial options phase. And to do that, you need to bring along your product-led delivery approach, which is bringing in the supply chain and contractors. Or if not necessarily bringing them on board, you need to have an understanding of what is available. So I think there's a bit of research needed at that stage as well. Then you want to look at actually what are the boundaries of these components. Should I just not be using them for some reason? Do they fit in with what I'm doing? And then, yeah, that feeds into an options report. And from a product point of view, you'd have a component performance specification. So once you know that these things can work, the performance spec, and you manufacture that component, and then it would come to site for the construction. So I've just looked at what are all the components of a bridge. So, you know, we have, and I've looked at, this is my personal thoughts, based on my experience, and, you know, do we have standard components in New Zealand for some of these things? And is there an ability to easily manufacture some of these items off-site rather than on-site? So for abutments and piers and pier crossheads, I don't think there's any standard components. I mean, yeah, we have the ability to manufacture precast columns, walls. You know, we have circular piers, precast concrete, but they're all bespoke elements for particular projects, and they usually require, you know, setup of some sort of precasting manufacturing capability or procurement of, I guess, formwork and works to actually build those elements. There's nothing standard that they've got things ready on site. And there's a challenge with New Zealand. You know, New Zealand is a seismic environment. Things are, you know, generally governed by the ground conditions, perhaps. So it is quite challenging to do this. Obviously, with pile caps and piles, generally these elements are, you know, in ground or at ground level, and usually they're very heavy components. So with retaining walls, yeah, there's plenty of retaining wall options out there. They're not necessarily structural. You know, a lot of MSC walls, block walls. There's a lot of actual products which you can buy, and it'll be essentially it's a standard component design and repeatable. And I think that's why some of them are very successful with a lot of the bridges we're building. With concrete barriers, yep, NZTA's got standard details and drawings for barriers, and they're precast offsite elements. Precast beams and steel beams are used widely. So I think, yes, there is some standard components. There's standard drawings for precast beams. For steel, there isn't. But they still requires, I guess, individual design to some extent of these elements. with bridge stick elements as well. Sorry, there's no component, but there is a lot of precast stick or half precast stick solutions being implemented. So also permanent formwork. This is another thing we sometimes use and sometimes don't use. I think there's probably a need for integrating that further into our designs as well, but it's not particularly common for actually civil structures. Another one is culverts. Yeah, plenty of precast concrete culverts, and they almost are a standard designed by suppliers. So I think where does digital engineering come into design, or working in a DfMA design approach? I think digital engineering enables the DfMA approach to be successful. If you're trying to build everything off-site, you need to understand how all of that's going to fit together and design it in 3D. And you can create components, and then you can easily repeat these components. Also, working with parametric design is something we're also doing quite a bit. Having repeatable elements. If you know that this one element can be repeated many times, you just model it once, and then you repeat it. So it's very, very easy and very efficient. I think you're also having the ability with working in 3D, you can alter your design and implement these changes rapidly if it is a parametric approach where everything is related to everything else in terms of the geometry. Also, we can exchange your parameters with architects and contractors. I think quite a few contractors now work in 3D. Maybe 5 to 10 years ago they didn't. Quite a few more now are working in 3D environments, and from what I can see, it's becoming the norm, or will become the norm. And also, obviously, you can present your design early stages and understand how things are built. So I'm just going to touch base on a few, examples within New Zealand, and then move on to one in the UK. So precast concrete beams. This is the Waterview ramp tunnels, ramp structures, and these are precast beams. These are all essentially precast beams off-site, brought to site and erected. You've got precast barriers as well here, just shown on the bottom here. And so I think this is, this method is almost required because other construction techniques are just not efficient. If you're looking at in situ versus the program benefits of maximising this sort of approach to in situ, it would be very significant, significantly longer. Another bridge down which Beca have worked on as well. Again, precast beams again with precast crossheads. So these are elements designed particularly for that project, but there's been on-site program benefits to adopting this way of working. So a few steel bridges. Steel bridges are very relatively common for bigger spans in New Zealand, or particular requirements. They're all fully manufactured in a shop and brought to site and erected. And I think that's the key way. Obviously, steel you're not going to build it on site, but that way of working also brings significant benefits. And particularly, we have precast concrete panels which sit on the bridge decks as well, which speeds up construction. So I think one thing we don't have, and I guess one area from what I've worked overseas on, is looking at, can we have substructure elements which are precast? How are they going to work in a New Zealand or seismic environment? They need to be durable. You want something that's lightweight, so it can be moved around from the production yard to on-site. It needs to be repetitive. It needs to actually accommodate a whole range of design scenarios. And obviously off-site is the precast concrete, is the precast formwork a way to go? Is there other ways of developing some sort of design? This image here is a precast permanent formwork design, which we worked on in the UK on the High Speed 2 project. And so this is essentially a Lego block type arrangement. You've got precast shells, and you stack them up, and you drop in a cage, and that cage can be designed for whatever design requirements you need, and you fill that up, and that's your permanent works in terms of what's in the void. The concrete is just the shell. It's not structural, it doesn't participate. But this way enabled the contractor to get huge significant time savings, and it's a repeatable modular element. So this is being implemented on a number of projects. So the High Speed 2 Enabling Works contract in the UK, which I worked on for a few years when I was over there, we adopted a DfMA approach for all bridge structures. I'm just going to quickly show a couple of them here. We had two weathering steel structures over the highway, and a couple rail bridges and a couple of road bridges over rail as well. And so we wanted to develop components which would fit in all of these bridges, and they're standard highway design. So you've got skews, all the different road constraints, etc. These are the first permanent structures on HS2 as well, which if you don't know about it, it's a £85 billion largest contract infrastructure project in Europe at the moment. So we adopted a DfMA approach on this. One of the bridges, a bridge over the M42, was fully built off-site for the whole superstructure. So the steel girders were obviously manufactured. We had full depth precast panels. So they were 300 mil thick precast concrete panels spanning between the beams, and then just an in-situ pour on the girder to tie them all together. We use SPMTs, so a self-propelled modular transporter, to essentially drive the entire superstructure down the road and only close the highway for 2 hours. Sorry, it was a bit longer than that, sorry. 2 hours to actually move it from its original construction position off-site down the highway and installed. And I think it was about a 1 day road closure, whereas that allowed for 2 days. And really early on, this approach to install it this way was the key decision was around, it's one of the busiest highways in the UK. I'm not sure what the traffic is, but it's probably 40, 50,000 vehicles a day. And yeah, just having any sort of temporary pier in the middle, two-span option. This is a 65 metre span actually, so a significant bridge. Anything in the middle to close down would just essentially, it's already terrible traffic at peak hour. Anything would just be significantly worse. So this option mitigated pretty much all impacts on the road network, which I think we don't necessarily consider sometimes if we're looking at just a two-span bridge. Why don't we go single span? Yeah, it might cost us a bit more, but actually the impact if it's a busy highway, I think it's almost invaluable. The other one, so there's two steel bridges, both very similar. So again, weathering steel girders, about a 49 metre span. This one took about just under an hour to drive down the highway and install it. And again, full depth precast panels, outer string course beams. They use steel parapets over there as well. So this is just a photo shown here of the bigger bridge being installed. And you can see on the abutment there, we've got our precast concrete abutments, a whole bunch of precast elements. So we've got, just kind of in the blue here, you've got the repeatable abutment shells, which are stacked up. You've got precast concrete sill beam, essentially, which is placed above that. All the back walls, they're all the screen wall or the back wall is all precast concrete as well. Even the bearing plinths are precast concrete bearing plinths. Obviously the steelworks off-site, all the deck elements are off-site as well. So yeah, if you have the right approach and the right facilities, you can achieve this. And I think, construction program is, when you're building the entire abutment, it might take them less than a week or a couple of days to place all of the precast abutment. In a normal in-situ world, you'd spend weeks doing all your temporary formwork and another few weeks or even months doing all your in-situ rebar. So you gain some significant benefits. So just before I finish up, just going to touch base on a couple of modular bridges, I guess, which are available. I've worked with Maybe Bridge before. They provide modular, repeatable steel truss designs. Another relatively new company in Australia, in quick bridging as well, where they have permanent formwork with in-situ concrete, but all of the geometry and everything is off-site manufactured in. And you can see in this bottom left picture, all the cages are all prefabricated and then brought to site and installed. So some significant time savings. I think it'll be interesting to see where these go in the future, or these sorts of bridges. They're not generally common at the moment from what I can see. So I think some challenges when you're trying to design elements to be precast or off-site manufactured. You need to have the right contractor engagement and client on board, and also technical approval authorities on board at the very beginning of the project. You need to have the right mindset. You need to design and build construction tolerances. If you don't think about construction tolerances, they won't fit on site. And also repetition of details means if you're looking at developing an element which is repeatable, if you do it in 3D, that can enable you to kind of proof check it, how does it fit? Because if you don't, then potentially you've got errors on site which you can't easily rectify. Sometimes with in situ concrete, you can just move things a bit and it works. With off-site or precast concrete or steel, you can't quite do that very easily. So just to wrap up, I think DfMA approach can provide many significant benefits to infrastructure projects, and is a way I guess I think we're starting to work more in. Digital design definitely enables this, and also enables us to do it quite rapidly and understand our designs. You need contractor involvement from the early phase, and also I think there's further development, or there is opportunity within the industry to develop more components to help trying to achieve our long-term goals of improving how we're delivering projects really in the construction sector in New Zealand. So thank you very much. That's me.
Well, it's probably got time for a couple of questions. I think, a couple of minutes left. I think we'll be really pretty full, but any questions for Liam? We've got to just ask, obviously some of those large assemblies, do you see any limitations on the sort of plant we typically have in New Zealand? Sort of craneage limits, particularly over a lot of our river bridges. See any issues there?
I guess those particular ones within the UK, they've got a lot more bigger plant, the SPMTs, which can move 2,000, 3,000 ton sort of weights. I guess here you've got to work with what your site constraint is. I think if there's an opportunity to have a more off-site approach, I think it's definitely one that should be considered.